for
Yeah.
Chris. Francis,
It was for a couple.
you got Kutzma. You got, if you want to get it done this fall.
But now I'm going
So anytime, Grant, whenever you're ready.
So, yeah, it was officially approved for whatever reason they didn't get it done.
Okay, so this is actually for the
And then the other one was,
I think that's not right.
Okay, I'll go ahead and get started. It's my distinct pleasure to welcome Gijs de Boer, alumnus from our department, back to give the colloquium talk today. Gijs was a graduate student at AOS from 2002 to 2009, working with Ed Almiranta on LiDAR and with Greg Tripoli as his academic advisor, looking, I guess, primarily at mixed phase stratus clouds and things of that type. And after he graduated with his PhD in 2009, I kind of lost view of what he was up to, but it turns out he spent a couple of years at the Lawrence Berkeley National Laboratory, and then pretty quickly went on to begin a career at the Cooperative Institute for Research in Environmental Science, or CIRIS, at CU Boulder. And he's been there ever since, but has basically been steadily advancing in his leadership role there, and has been very deeply involved in a variety of interesting projects there. I became aware and started to catch up a little bit with everything Gijs has been doing when I went to a workshop in February 2017 out of Boulder relating to the use of drones in the atmospheric sciences. And at that point, I became aware that was a new focus of the direction that his work had been taking. And that's what he'll be talking about today. Gijs holds a leadership position, or leadership positions, in connection with a number of national and international research programs related at least partially to high latitude climate. And he recently became the Associate Director and Chief Scientist for Integrated Remote and In Situ Sensing. He is the author, co-author on 13 publications just this current year, and well over 56 overall since leaving the program here, and has been involved in about a dozen field campaigns. His research interests include cloud microphysics, Arctic weather and climate, boundary layer physics, unmanned aircraft systems for atmospheric research, and atmospheric remote sensing. And with that, I'd like to welcome Gijs, and I look forward to your talk.
Great, yeah, thank you, Grant. The microphone working okay?
Is it unmuted?
Never had a mic on with, no, it's not muted at the moment. People in the back hear me okay? Okay, great. It's my first presentation with a mask on, so it's also my first talk back since we all kind of disappeared for a little bit in March of 2020. And so it's really nice to be able to do that in a comfortable environment here. I've had plenty of presentations in this room, although it looks a little different than 12 years ago or so. But as Grant mentioned, I have a variety of different roles at the University of Colorado. Primarily, I'm a research scientist at CIRIS. I've been doing that for a little over 10 years now. I do have an administrative role in IRIS, which is a program that's primarily housed in the aerospace engineering department on campus at CU, but is focused on Earth system sensing with innovative observing technologies. And then the last role I'll mention really quickly, I'm a founder of a consulting company, and the reason I bring this up is primarily to let you know that one of the companies that I have worked with in the past as a consultant is also one that we work with in our research. And so Blacksmith Technologies is a name you'll hear. It's a company that I have consulted for, and I'm required to disclose it, but I also want to make sure that everybody's aware of that so that it doesn't seem like there's a conflict of interest there. All right, so the last time I was in this room, I think this was one of the last images I showed. And for some of you, it may look familiar. For most of you, probably not. But this is kind of how my path towards using UAS started a long time ago. At that time, as Grant mentioned, I was very focused on high latitude clouds and specifically stratiform mixed phase clouds in the Arctic. And these are some figures that Greg probably recognizes from when we were running NMS to look at how well we can simulate some of these clouds and try to recreate some of the observational things that we had available to us at that time. And it was through this work and what happened afterward that I connected with a variety of co-authors in 2012 on a review paper that we had published in Nature Geophysics on these types of clouds, or geosciences, excuse me, on these types of clouds. and all of the complex processes that are in place to help maintain their life cycle. In doing so, we started developing figures like this one, and I started thinking more about where our gaps in understanding were, and how we might be able to address those. And it became obvious to me pretty quickly that from an observing perspective, a lot of our gaps were in getting in situ observations in environments like this for some of the key processes. So thinking about the dynamics of the turbulence that help to maintain the clouds, some of the radiative structure at the cloud top in particular, where that cooling is forcing this dynamic circulation within the cloud layer. Similarly, the turbulent fluxes at the surface and how those go to support the input into the system in general, and particularly in a place like the Arctic where we have such a complex surface environment and a lot of different variability between sea ice, open water, snow-covered land and not. Aerosol processes also super important, and we always have these great aerosol observations at the surface, but really hard to do that aloft without bringing a bunch of research aircraft into the mix. So thinking about all that, I really tried to figure out how can we do this without having to spend hundreds of thousands, if not millions of dollars to get a research airplane up there every time we have a specific question. And what I came to was that we had some technologies in place that could help us with a lot of these questions that require getting up off the ground and getting some detailed measurements at the cloud height or within the mixed layer associated with that cloud. And so I started moving towards remotely piloted aircraft systems. And you know, for people, that means different things. So whenever you say the word drones, you can tell almost by the reaction you get in the person's eyes as to what side of the fence they are on. Some people get very offended and they think of all the military applications and all the things that we're doing in the world that really are not appreciated by a lot of different people. And other people think about these things. And some of you in the room may have small, kind of commercially available drones in your own houses that you fly on a regular basis. There are lots of different types of platforms out there. For today's talk, I'm talking mainly about something that's kind of in between. These are what the FAA terms to be small UAS, under 55 pounds, and typically at a scale that's kind of comparable to a person. Yeah?
Is that under 55 or under 0.55?
Sorry, the micro, these ones are 0.55.
Oh, okay, got it.
So, my fault. I should have pointed out what was going on the left side there, but or on the right side for you.
It just seems really light.
Yeah, it is really light, and it's a special category within the FAA, which is why I bring it up. But in general, you know, the platforms that I'm talking about here are kind of in between. They're not the huge military type of drones, are the ones that NASA operates for system research. It's also not the teeny tiny consumer type drones that really can't carry very much other than a camera. But it's something, and I'll show you a few examples that kind of falls between those things. And before I dive too much into specifics, I thought I'd spend a couple minutes here talking about just the case for these types of platforms. There are lots of different ways that these can be used, and there are some very distinct advantages in my eyes on why we can use these platforms and why we should use these platforms. For one, the operational footprint is quite small. Right? For a lot of these platforms, I'm going to let this loop in the background here for a little bit. You can operate these with 2 people. I mean, technically with 1, although that gets a little bit tricky from all the roles you have to cover. You can get out there with a launcher and a tent and a laptop, and you've got all the equipment you need to fly the aircraft. And as you see in the next video, you know, you can set yourself up to be quite mobile. We have vehicles that have launching systems and all the electronics inside the vehicle, so we can go out with a Ford Explorer and have everything we need to be out in the field and getting things in the air in short order. That's one good thing. I'll also point out, this guy, he's an undergraduate student that joined us for a field campaign not too long ago. These are fantastic tools for students. There's a lot of hands-on accessibility. There's also a lot of ways that you can get out in the field and have good experiences with research equipment with this sort of thing, which is a little bit more difficult when it comes to larger aircraft, just because of the constraints on access and availability. Another advantage that I'll show you, and I apologize if anyone gets seasick, you might want to look away a little bit because we're flying in a convective boundary layer here and bouncing around a little bit. But these systems tend to fly fairly slowly. For most of the platforms, that's a cruise speed of between about 14 and 20 meters per second. And some people may see that as a disadvantage because you can't cover quite as much ground, but the reality is, for a lot of the processes that we look to study with these platforms, it's really advantageous to not blast through them at hundreds of meters per second. You have much better resolution on what's going on. In this instance, we were flying over southeastern Wisconsin at the Chilwaukee Prairie State Wildlife Area, right on the Lake Michigan coastline, looking at lake breeze circulations and their impact on air quality. And we wanted to spend as much time as possible within that lake breeze layer and right at the interface above it so that we can look at the turbulence and the dynamics of the circulation and its impacts on the air quality in that environment. And with the sensors that we fly on these aircraft, we get resolutions for some of our measurements down to centimeter scales, right? So much higher resolution than in any model that we're running on a regular basis. And we can fly these over scales of tens of kilometers, so you get a really broad range of different conditions that you can sample. The final note I'll make is that because these platforms tend to be somewhat inexpensive and they don't contain any people, we can fly them in what are typically very high-risk environments. And so this is an example of Supercell Intercepts that we conducted, flying around. We were trying to understand some of the dynamics of that environment. We've also flown these at low altitude over the sea ice. You know, Grant's a pilot. Grant, if I were to ask you, do you want to fly 20 meters over the sea ice offshore for hours at a time, you would say, no, thank you.
That sounds like fun.
Yeah. It's just, you can put these things in places that you wouldn't want to put people because of the potential risk, or that you would want to put very, very expensive equipment just because you might not see it now. So I wish I could say I'm the first one to do this. I'm definitely not the first one to do this. People have been flying this scale of aircraft for atmospheric science for several decades, dating back to the 1970s. And there's a lot of innovation that's happened, right? We're in kind of what I like to call a golden age of just microscale stuff. We've got computers in our pockets. I've got a watch on that can tell me everything about how my run went today. Things are shrinking, and we're riding that wave for sure with these aircraft. Everything is getting more accessible. We can put more powerful computing equipment on board the aircraft to do onboard processing of data if we want to. All of our communications equipment has benefited from these types of technologies. And certainly, a lot of the stuff that happened in the 70s, 80s, 90s, and even early 2000s, we have way greater capabilities now because of all these advancements in our cell phone technology, which is really nice. And so, making the transition here, when I moved from Berkeley Lab to the University of Colorado and started thinking about UAS, I was really fortunate to land in a place where this is not totally a new thing. And I've worked with a lot of people, many of whom are actually not on this slide. This is kind of the current cast of collaborators that I'm working with on a daily basis for a lot of these UAS-based projects. But specifically, Brian Argrove, Dale Lawrence, Steve Borenstein, they are all on the aerospace engineering side of the house. They have been working with UAS for atmospheric science since the early 2000s. And Brian in particular has done a lot of work with the University of Nebraska and other groups on severe storms research. And so tapping into that amount of expertise, I've taken these technologies to different places and not just focused on the severe storms, but thought about the Arctic, tropical conditions. We'll get into some of the details here in a minute. But I do want to take a second to acknowledge all of these people, as well as the funding agencies that have supported what's happened here over the last couple of years, for a decade or so. All right, so with all that in mind, a quick whirlwind tour of what I've been up to in the last 10 years. We started out in 2013 writing a proposal to the Department of Energy to operate small UAS up on the North Slope of Alaska. Seemed like a good idea, right? That's where my research background was. I was into the Arctic. Why not? Turns out that that's one of the more challenging places to fly these things. But in general, I think it was a very successful set of campaigns. We started out with these two platforms. The Data Hawk, which is this airplane. This is about a 1.2 meter wingspan, something like this. And then the Pilatus, which is a larger aircraft. This is a kind of a kit model aircraft that we just worked to integrate a whole bunch of instrumentation on. That plane we flew at almost exactly 55 pounds, kind of the upper limit of the FAA limits for small UAS. I won't provide too many details here, but a couple of things to note. This plane flies for about 45 or 50 minutes. That plane, in that configuration and that weight, we did make it an electric airplane from fuel. which really limited the amount of time we can be in the air with it, and that was a big problem for us. But we felt like we had to do that, one, because transporting fuel around all the time is a real pain, and two, because we were making aerosol measurements and we didn't want to be polluting our own data streams. So those are a couple of the platforms. I'll get into some examples of what we were doing up there. But those early campaigns stretched from 2014 all the way into late 2017 and early 2018 through very direct collaboration with the DOE ARM program, who were also trying to redefine what they did with the UAS. They have been involved with unmanned aircraft for a long time, but more on the larger, big platform side. And they were trying to decide whether they also wanted to go into the small UAS realm to get some more kind of nimble sampling strategies. We went up to Littock Point, Alaska, which is the orange dot here, right on the north slope, in part because there was a new ARM facility being installed there, but also because the Department of Energy manages restricted airspace in that area. So the airspace and permissions issues became a lot simpler for us. We just had to well, maybe not simpler, because we had to satisfy the Department of Energy. That might have actually been more complicated than the FAA. But we got it done. And these campaigns, I would say, were very successful, partly because we did collect quite a lot of data, but also partly because it was a huge learning experience for us in our journey onward. We learned about the weather and operating in harsh environments like this, icing, how our aircraft perform in adverse conditions. We also learned about operating with bears, both brown and white bears, and what sort of conditions we needed to be ready for there. But all in all, this supported both our own work and our own advancement with our platforms, as well as the Department of Energy's advancement in using UAS technologies. So I thought this went very well. A couple of examples of some of the sorts of data sets that we were collecting. The DataHawk is set up as a thermodynamic profiler. It can also make estimates of wind properties, other kind of mean wind properties. It's not really set up for turbulence measurements. And just as an example, this is a case where we were flying in October, and this is right as the sea ice is starting to form. We had this beautiful blue day, clear day, and that came along with some really strong near-surface temperature inversions. So there's really strong radiative cooling going on. And on this particular day, we had this kind of kicking off the ice formation process in the sea ice. And so we had the strong lower atmospheric stability. The next day was quite different. So the next day we had significant cloud cover. And this is the sort of cloud that I grew up studying here in Madison, right? These low-level stratiform clouds. And that has major implications on the thermodynamic structure. You can see we've got cloud-driven mixed layer that sets up below the cloud, and the cloud is also warming the surface, and we have shear-induced mixing at the surface as well. So putting all those pieces together, you can see this transition of the different boundary layer structure and the lower atmospheric structure over time. We've used this for a variety of purposes, partly to just look at how well we can simulate some of these processes, but also for understanding stable boundary layer conditions. These figures are from a paper from Peter Sullivan at NCAR, where they were simulating with LES these really stable regimes. And one of the things that they wrote about was the presence of these kind of intermittent or spurious mixed layers transitioning their way through the simulation domain, and trying to understand what sort of dynamics in the stable boundary layer are forcing intermittent turbulence and intermittent mixing within the layer. So we went to our own UAS data to see whether we saw anything similar, and sure enough, we do. So this is, again, from that October case, really strong temperature inversion. You know, you got, what is that, almost 7 degrees here over about 50 meters, 100 meters. And then we get something that looks like this, right? These are those low mix layers that are kind of advecting their way through. The colors here are time, right? So over time, you can see the transition of these layers throughout the atmosphere. Different scales, too. You have slightly deeper low mix layers here, or smaller ones that are kind of making their way through. And so this is work that is currently being undertaken by Brian Butterworth, who I think many of you might know. He was here working with Uncrewed for some time on cheesehead science. He just joined our group. And just as an initial perspective, he's starting to look at what sort of things might be driving these mixing events. And our initial hypothesis is that it's largely connected to the shear from the low-level jet that sets up in these types of environments. And that seems to be consistent across many of these cases. I also showed the Pilatus earlier, and I just want to provide a couple of examples of sorts of measurements we're making with that platform. On the left here, one of the things that we benefited from is close collaboration with the NOAA Chemical Sciences Laboratory, which is just down the hall from where I sit at the Physical Sciences Laboratory. And they were prototyping instruments that they were developing specifically for UAS applications. In this case, this is the POPS instrument. It's an optical spectrometer that's set up to make measurements of particle size distribution. So we got some initial measurements with that system, profiling what the aerosol structure looked like throughout the atmosphere. So you've got the size distribution at different altitudes. You've got it kind of plotted out over here as well in different phases. And then just a mean concentration with height. And this sort of information in the Arctic in particular is very important for trying to understand some of the cloud processes, because we do have oftentimes in decoupled cloud situations where the surface measurements aren't really representative for what's going on at the cloud height. On the other side of the screen, we have some of the initial radiation measurements that we were taking with, in this case, the SPN1 pyranometer. And this is kind of a unique system that was developed specifically to be able to distinguish between the direct and the diffuse components of the radiation. Turns out that that's critical when you're doing this from a moving platform, because you have to go back and correct for that motion and the angle relative to the sun, and you can't really do that without being able to distinguish these things. I will say that the radiation stuff from the fixed wing was not super successful, and I'll show you why in a few minutes as we get back to some of the other platforms.
Guys, just a quick technical question. Was it on a stabilized?
No, it wasn't. So we had two on the top, one on the bottom. We weren't so worried about the direct diffuse part of the bottom, but up on top, we wanted to make sure that we can distinguish between those and then correct based on our knowledge of where the sun was for the offset relative to the sun. And we were working on this with Chuck Long, who had developed a similar algorithm for the G1 aircraft that DOE operates. But as I'll get into in a minute, flying this thing at altitude, you start to aggregate a lot of the scales that you're interested in, just because you have such a large field of view with the sensors. So I'll talk more about that. So as a result of some of this initial work, I got involved with a group called ISRA, and ISRA is the International Society for Atmospheric Research with remotely piloted aircraft. We've been meeting annually since 2013, and in 2018, I was fortunate enough to work with a variety of sponsors to bring that meeting to Boulder, and we had about 150 of the world's experts in this subject matter join us in Colorado to talk about all things atmospheric science with UAS. On the flip side, on the back side of that meeting, though, we also decided that it would be really fun if a lot of those people would bring their systems with them, and we could do a flight week. So we went down to the San Luis Valley in south central Colorado, a big wide open area with several teams, mostly domestic teams, just because it was hard to get stuff over here from overseas, but namely Nebraska, University of Kentucky, Oklahoma State, Blacksmith was there. Who else? Oh, Virginia Tech. We had a big group of people, and over the course of about 4.5 days, we collected over 1,000 flight hours between all of our platforms, which is an insane amount of flying, but a lot of fun. And we were targeting a few different phenomena. Again, this was all kind of brought together as part of this meeting, but we decided to pick some specific science targets, and those included the morning boundary layer transition in this valley. It's a high altitude valley. You get very strong radiative cooling at night, and then good solar exposure during the day, so you get a really nice transition. Convective initiation over this valley region. You've got tall peaks all around, so it's very regular, or very common to get good convection and cloud cover over those mountains, but not very much happening over the valley. And so in this particular instance, we were interested in trying to understand cases where we might get convection over the valley and what would set that off. And then finally, drainage flows. We've got some of these narrower valleys coming into the big valley, trying to understand nocturnal and early morning drainage density currents coming down those valleys. And so I'll show a couple of examples of data from those studies. I'm talking about the drainage flows. Here are some figures from the aircraft that were positioned in the Sawatch Valley, which is in the kind of northwest corner. You can see on the map there, the PG and SA sites are in that narrow corner there. Capturing what was not quite as strong of a drainage event as we would have liked because we had some high cloud cover the night before we were going to do this. But still a pretty good event. You can see clearly the temperature gradients that are setting up, as well as some of the velocity, the wind structure, and some of the unique elements of the UAS come out here, right? We have different heights, 100 meters, 150 meters, that we're looking at the cross-sectional variability throughout the valley. Where, you know, with a remote sensor or with a radiosonde, you get one nice single profile in the middle. Here we're able to fly back and forth across the valley at different heights and capture the three-dimensional structure with these platforms. And so we're using these data now to evaluate some of the 1D and 2D models that are out there to understand how these flows work relative to what we're observing. We're also working with our partners at NCAR, namely Anders Jensen and James Pinto, to assess to what extent we might be able to assimilate some of these UAS data into high-resolution simulations. In this case, they're using WRF with the 1 kilometer domain and have it set up over the San Luis Valley. We've got platforms all over the place. And so they ran some sensitivity experiments that included assimilation of the UAS data or surface met or both. The left panels here show the results at 2 altitudes, 13 and 116 meters, of the kind of occurrence of that drainage flow within the domain that they're looking at. And you can see that bringing the UAS data in really changes the structure of that flow and the intensity of that flow. And the right side shows comparison to LiDAR data on the top, wind LiDAR data of the impact of the assimilation of that UAS data. So we're continuing these types of studies. We did some similar work with the convective initiation question, looking at where the precipitation and the cloud cover forms over the valley with the UAS measurements, and we showed there that the boundary conditions that we were using from her, in this case, were not really capturing the vertical structure of the moisture field very well, and that really impacted the ability of the model to kick off any convection in certain parts of the valley, whereas when we brought the UAS measurements in, and for this campaign we had authorization to fly up to 1 kilometer above the surface, so we got pretty good moisture profiles extending well into the boundary layer. That helped out. Yeah, great.
What's the resolution you used in that?
For
You said 1 kilometer inner domain.
sorry, that's the resolution. It's a 1
That's the
kilometer
resolution.
grid spacing. Yeah, I don't remember the dimensions of the inner domain, but it covered more than what you're seeing here. There's a paper, the Jensen et al. Paper I can point you to if you want to follow.
That's kind of insufficient to see large eddy.
No, that's correct, yeah.
Yeah.
Yeah, but in this instance, we weren't really looking for large eddies for the drainage flow in particular. It was really the pooling of air from the terrain, and we had enough resolution to capture that terrain. Another thing we were able to do during lapse rate is some really detailed intercomparison between systems and some ground-based observations we had out there. This is our University of Colorado MERC vehicle, which has a 50-foot mast on it. So we were able to fly platforms next to that mast and do comparisons to that, as well as to some of the remote sensing tools that were out there. I won't get into all these details. There's a lot going on in these figures, but a couple things that we learned there. One, the sensor integration is super important. We had several instances where people were flying the same exact sensors on different platforms, and the way that those sensors were integrated with the aircraft. This might seem like a common sense statement, but the reality is everybody thought that they had done the integration the right way. And yet, there were instances where you would get 2-degree differences between platforms using the same exact sensors just because of where on the aircraft and how on the aircraft those things were integrated. And just the need for kind of some common guidelines, and Grant and I talked about this a little bit earlier. As a community, you know, it's really important, of course, that we provide the best measurements we can, and we want to make sure that we're providing good measurements. So having some guidelines for the community. One of the things that I walked away with was this need, again, for kind of a common sensing system. So with some support from NOAA, I started working on a miniaturized sensing system that was designed for thermodynamic, wind, and flux profiling. And it's called Miniflux. This is a system that we have now signed operational transition plan with NOAA for, and it's set up with up and downward looking IR thermometers, so you get an idea of when you're flying under cloud or what sort of surface variability you have underneath the aircraft. A multi-hole pressure probe to used to measure the angle of attack and the side slip angles of the airflow over the sensor package. That helps us with our wind estimation. A bunch of temperature sensors and humidity sensors, and then the guts to tell us kind of what the attitude of the aircraft is, how it's moving through the air, its position, and then an onboard data logging computer. And this thing is about this scale, and it's set up that you can transfer it from one plane to the next, with the idea being that if this system is well characterized, and we're kind of integrating it the same way from one airplane to the next, that we should get consistent measurements out of that. And since that time, we have deployed this a couple times, once partnering with the University of Alaska Fairbanks to participate in the stratified ocean dynamics of the Arctic experiment over northern Alaska. Here the idea was to fly the aircraft offshore and significant distances offshore, hundreds of nautical miles, to capture the transition between coastal Alaska, the land-fast ice, and then the marginal ice zone offshore, and better understand the dynamics that are driving what's happening at the surface. And there were research vessels out there. There were a lot of autonomous buoys and other observing capabilities down at the surface. So that was one example of what we were doing up there. And then more recently, again, we've been working with NOAA to integrate it onto this platform. This is the FBR-55 that's built by L3Harris Technologies. And of course, a unique capability here with the vertical takeoff and landing. I think this is a fantastic platform because it allows us to operate this from very small footprints, without a runway, without a lot of distance to take off from. You know, you can think of tree canopies, you can also think of ships, and that was the primary purpose that NOAA was thinking of for this platform, was to be able to fly it off the deck of their research vessels. It is the only way that we can get near-surface observations over the remote oceans. I mean, there aren't any research aircraft that are ready to spend a lot of time down at 100 meters or less when they're 8 hours offshore. They're just not going to do that. So this sort of a platform can provide some really unique perspectives in parts of the world that are otherwise pretty inaccessible. Internally, we took the Miniflux payload and decided that we needed a new aircraft. And that was out of a need that came out of some of the severe storms work that I was alluding to earlier, where every second is super valuable. You don't have a lot of time to react. It can't take a half hour or 40 minutes to get a plane up in the sky, because by that time the storm has moved on and you've missed it. And so the engineers that I work with at IRIS were tasked with designing a system that can be deployed in about 5 minutes. So that I showed you the vehicle launch earlier. That vehicle can pull up on a roadside, get the plane out, put it on the launcher, do your initial checks, and send it off. And so that's where the Raven was born. And Raven was equipped, you can see a lot of the familiar parts from the Miniflux that I showed you a couple minutes ago. The multi-hole pressure probe is here. This is a fine wire sensor for turbulence measurements. You have a cold wire and a hot wire anemometer on board. We've got dual temperature, humidity, pressure sensors from Wisco on board, and then those IR thermometers up and down looking. All those pieces were integrated onto Raven, and it's become our workhorse. As an aside, a current project that we have as part of the outreach, we started developing superheroes for all of our instrumentation. So that's Winged Wonder, aka Raven. There'll be a couple more that come up along the way here. I was talking about the sensor and system evaluation earlier. This is some of our initial work for Raven. Raven first flew operationally in 2018, so this is all fairly recent, but we took time and the opportunities to fly at a couple of different facilities. On the left here, we're comparing the Raven wind measurements to those from an instrumented tower at the NREL National Wind Technology Center, which is just south of Boulder. So you can see for both wind speed and direction, the red curve is the Raven observations. The black and green are what were being measured by a sonic anemometer at the same height over that time record. And then the 4 panels on the right-hand side are a comparison that we conducted earlier this year at the Southern Great Plains facility that the DOE operates, with a few different aircraft, including the Raven, which is all the yellow dots that you see, the Black Swift S2, sorry, that should be S0, excuse me, and then the University of Oklahoma Copter Sonde and the University of Nebraska Meteor Drone and M600 platforms. You do see quite a bit of scatter. I mean, in general, I think everyone was relatively happy with what they collected. In this case, we're comparing to radiosondes, so the radiosonde would be launched and we start chasing it, just go up right behind it. But from the Raven side, I'm very proud of where those yellow dots fall on the plots, and gives us confidence that we can move forward with this as a research-grade platform and get it out of the community to support whatever science is out there. One of the projects that we supported with Raven in early 2020, right before the pandemic, was Atomic. And Atomic was a sister project to the Eureka campaign taking place in the tropical Atlantic, or over the tropical Atlantic. We were supposed to be doing this using that FVR, the vertical takeoff and landing system that I showed earlier, from the NOAA Ron Brown vessel, and we were supposed to be hundreds of miles offshore. Unfortunately, the aircraft wasn't quite ready, so we kind of jumped into action and said, well, we have this other platform that we've been developing, we would love to still deploy something. And we flew in northeastern Barbados, right from the beach. It was rough, it was terrible. I hope I never have to do it again. But we were flying very regular flights over about a month of time in the nearshore environment on the upwind side of the island. So we had trade winds coming straight in off of the ocean. And we were flying on a daily basis, 2 flights per day, 1 in the morning, 1 in the afternoon. And this was our general flight pattern. We would start with a profile up to 1 kilometer and back down to just below cloud base. And then we'd spend about 20 minutes below cloud base to collect statistics there, and then slowly step down 400 meters, 200 meters, 20 meters, so that we can get profiles of turbulent fluxes of heat momentum, for example. We can get information on the variability taking place within each of these layers and how that changes. So this was great, and here's some examples of the sort of data that we're collecting. Here looking at the range of variability of temperature at a given altitude, right? So this is 20 meters, 500 meters. Just one example, one flight. We got 37 flights worth of this, but thinking about how much variability there is at the local scales at a given altitude, whether we capture some of that variability adequately with our modeling tools is an open question, I think. Or with the parameterizations that we use. Similarly, vertical velocity structure, right? So here we're looking at vertical velocities, different altitudes, 500 meters or 200 meters, or with conditions with clouds overhead, and this is where that IR thermometer becomes very useful because we can see exactly when we're under a cloud flying through the lower atmosphere. You can see it's a very different shape, of course, with the clouds, as you would expect. You see more positive vertical velocities in the updrafts under cloud structure. And then thinking about turbulent fluxes, this is momentum flux near the surface. This is from all of our 20-meter measurements over the course of the campaign. So looking at that as a function of the wind speed near the surface. And then, of course, uniquely with the aircraft, we can provide profiles of that through the subcloud layer. And we're currently collaborating with our Dutch collaborators to understand this momentum budget for tropical trade wind cumulus clouds and try to better understand what makes those clouds tick. So I'm broadening my cloud portfolio a little bit. I'm still learning about the tropical clouds, so please don't quiz me too much on all that. But it's really nice to find applications for the types of measurements that we're collecting that can support additional information on some of these types of cloud structures. Another recent campaign that we worked as part of was Mosaic. Mosaic is the multidisciplinary drifting observatory for the study of Arctic climate, and this is, hopefully some of you at least are familiar with Mosaic, but for those who aren't, it was a 1-year drift on an icebreaker through the Arctic, and the different colors here are the different legs of Mosaic, starting with leg 1 and 2 here in blue, leg 3, leg 4, and then leg 5 is the dark blue, and they kind of got spit out of the ice a little early, so they motored back in and went back up to the North Pole, which is why there's that discontinuity there. But for our part of Mosaic, we were tasked with operating these types of drones from the near ice environment around the ship. And so our flights took place where you see the dots here. We took up the data hawk that I showed earlier, as well as a helix. I'll talk about the helix in a second. And conducted flights as far north as about 87 degrees north, and then down just to the west of Svalbard here to look at boundary layer structure and surface variability. So this is lower atmospheric structure from Mosaic in a nutshell. Just an example of the sorts of conditions that we sampled for leg 3 and leg 4. And this is what I love about the Arctic. A little bit of an aside, right? This is the sort of variability that we see in the Arctic. huge inversions. We see these warm air intrusion events, right, where the surface is pinned to freezing because of the ice that's in place and the melting that's going on, and these really warm conditions aloft due to transport from lower latitudes. We also saw some of these earlier on. It wasn't quite as warm, but again, some of these events were warm air intrusion events. A lot going on with those already, several studies that are looking at how those impact the surface energy budget, right? What's the influence on both the radiative and turbulent fluxes of the surface as a result of this warm air that's just sitting right above the surface, as well as studies on the air quality and the aerosol. As we get these intrusion events, you see the increases in aerosol. Is that the result of a shrinking boundary layer? Is that the result of entrainment into the lower atmosphere from whatever's being ejected below? There's a ton of data from Mosaic to dig into. One of the other things that we did there was try to understand the influence of leads, these cracks in the ice, on the lower atmospheric structure. And I'll be honest and say we didn't get the huge, beautiful lead right next to the ship that we were hoping for, but we did get a lot of these smaller ones. And at some level, I think the small ones need to be considered in terms of their importance because there are way more of them. Right? The big ones are the ones you can see from the satellite, but there are way more small cracks like this. And so we would fly the data hawk both sides of the lead, and this is something that one of our undergraduate students is working on right now, but looking at the upwind side versus the downwind side, what sort of structural differences there are there in the profiles. It's certainly early on, and I'll say early on, we don't see a lot of structural differences. A lot of the stuff up here is not the result of the lead. In fact, the downwind side tends to be cooler in this instance. So we're trying to pull all this apart and better understand what's going on near the surface from an energy transport perspective and energy flux perspective that might help to drive any differences that we do see in the profiles. So Helix, here's another one of our superheroes, the Buzz. This is a hexacopter, and most of the work that we do is with fixed-wing platforms, but I talked earlier about the radiation measurements and what we were trying to do with the UAS. This is an example of how technology is evolving very quickly. Back in 2014, there were multicopters like this, but they typically had about a 10-minute endurance, and they couldn't carry very much. And the battery technology has evolved, and the drone technology has evolved to the point where now we can take this platform and instrument it with 2 gimbals up and down. So here's your stabilization, Grant. We worked with Kip and Zonin to develop some special, it's kind of like a PR1 pyranometer, but lighter weight. So they went to 3D printed parts on some of this stuff so that we can put it on the drone. We're also flying a downward-looking multispectral camera, get imagery of what it is we're flying over. And we get about the same amount of flight time with this as we did with the fixed-wing Pilatus 6 years ago. And so it makes a lot of sense here to go to this platform because we can hover over features of interest, we can fly at a lower altitude and a slower speed, and we can still cover a lot of the same ground at a much lower altitude with respect to the ice surface itself.
What's the endurance on that?
It's about 25 minutes. Yeah. But also of advantage here, and you can see in the photo, when we were flying at Mosaic in the summertime, the ice was really starting to melt. We had a lot of melt ponds, very little solid ice to work on, and so something like the Pilatus was never in play here because we would need a runway, and we don't have a runway. And so something like this with a vertical takeoff and landing is very powerful in being able to tackle some of our measurement objectives in this type of environment. Some of the things that we're doing with the Helix data, I talked earlier about with the Pilatus, there being kind of aggregation of scales as we get higher in the atmosphere because of the field of view of the sensor that we're flying. These figures here kind of illustrate that problem, right? You have profiles. This is the upwelling irradiance from the downward-looking sensor versus altitude, and you can see that there's this very clear split that's taking place at the interface between melt ponds and snow. So, flying over the pond versus over the snow surface. At low altitude, when you're down low over the snow, you're sampling the albedo of snow. If you're right next to it over the pond, you're sampling the albedo of the pond, and as you go up, you start to aggregate all these different scales together into what is kind of a common albedo value. And the question is, what's important to you, right? If you want a representative value for a large footprint, this is your number. If you want the detailed variability that's happening near the surface, then these are your numbers. It guides what altitude you might want to fly at, capture that information. And it also helps you to better understand the different scales involved. So if you fly at the low altitude, especially when you have the imagery, you can start to look at the contributions of different scales of features, whether it's melt ponds or snow-covered ice versus bare ice or whatever the case may be, and understand how that all aggregates into the albedo that should be used to represent a certain surface. And this is something that we're working with Marika Holland and others at NCAR, Don Perovich, to try to leverage these data and try to understand whether the albedo parameterizations or the sea ice parameterizations are adequately representing this sort of variability and its potential impact on the surface energy budget. So I just talked about the length scales. I won't get much more into detail, but just an example of how the imagery that we collect can be used. This is just for one flight. We can use the reflectance maps from the multispectral camera to try to identify certain feature types. In this case, you can see very clearly that the melt ponds jump out in those red features. And then we can look at different pixels, different scales, different aggregation scales, just within a given map, and try to understand, what scales that sort of variability exists at. So if we were to take a box of roughly this and do that in all the different places in this map and run it through a bunch of maps, you can see the evolution of the scales. And the ice is an evolving entity, particularly in the summertime. You get these melt ponds that set up. Sometimes the melt pond drains through the bottom and all the melt water disappears and all of a sudden it's bright white again because it's just ice. Other times you get refreezing of the melt ponds at night and you get snow that falls on top of that and all the melt ponds disappear. So we can capture the evolution of some of these processes with these regular flights. At the same time, we can capture very detailed measurements over the domain, looking at different feature types by hovering in place over a given feature type at low altitude. So, a ridge, snow-covered ridge, sediment-covered snow, a little bit lower albedo there. Clearly the melt pond and the ocean are quite dark. And we can start to build a library and inventory over different flights of how those albedo values are varying over the summer season. All right, so the last campaign I'll talk about here from recent work is Wisco Disco. This is something that, Disco, by the way, is the dynamic impacts of Disco. Brad, you want to help me?
I can't remember.
Dynamic impacts of shoreline circulations on ozone.
There you go.
And this was focused on the Lake Michigan shoreline. I showed you the flight earlier, and trying to understand how pollution events in southeastern Wisconsin, in this particular instance, are driven by some of these shoreline circulations, and specifically, all of the emissions coming from Chicago, Gary, southern Lake Michigan, that are evected out of the lake, left there to simmer and process, and then sloshed around by the coastal circulation. How that impacts high-level pollution events in the coastal counties and coastal environments. And so here we operated the Raven. You saw the video earlier, doing both coastal transects across the gradient, ducking in and out of the lake breeze. You can see here, it's kind of the marine, call it the marine layer, it's a lake layer, but very clearly set up just offshore in this case, and we're kind of ducking in and out of it, and just in a short time span here, about 15 minutes, you can see that layer kind of eroding and getting pushed offshore. And at the same time, we have observations on the coastline of ozone, both from a profiling system, a UAS, as well as down at the surface, and a wind LiDAR. So we have pretty good coverage of trying to understand what's going on in the near coastal zone. And the UAS observations were there to really support getting these gradients, trying to understand how those interplay with one another, and also start to, again, derive these profiles of certain mixing parameters. And you can see on the far right there, you have profiles of theta V and water vapor, and you can see the variability, right? You can see where it is that we held our altitude for a while. And you get a single profile just by going up and down, but then you get all this variability when you hold in place that exists that you don't pick up with a single profile. And it's in this variability that we try to estimate some of the fluxes of heat and momentum through the layer, and then particularly down low, where we did duck in and out of the lake breeze here. You can see the huge amount of variability down here on the surface because of that lake breeze pushing into our sampling domain. Trying to understand fluxes across the interface between the background flow and the lake breeze. So a little bit of forward-looking statements. We've got a bunch of different stuff currently active and coming up. For one thing, we are working with our partners at the University of Oklahoma, Brookhaven, and other institutes to contribute to the Tracer campaign. This is taking place now next summer. It was supposed to be this summer, but they delayed it by a year, in the Houston area. And with the Raven, again, kind of targeting this coastal environment and all the complex interactions that are going on as the sea breeze, the Gulf breeze is pushing its way inland, driving frontal zone and kind of convective enhancement. I didn't show the satellite image here, but you can often see enhancement of the convection right at this interface where the Gulf breeze and the background flow are colliding with one another. Also very different aerosol properties, so we're going to put a POPs on the Raven as well for these flights and capture a lot of the different physical processes that are going on kind of between the Gulf of Mexico shoreline and the city of Houston. Upper right, Splash. This is a project that I'm super excited about, partly because I'm the PI for the project, so I have to be super excited about it, but also partly because it's in my own backyard. We're going to be spending a year in Crested Butte, and we have instrumentation in place as of this fall. Here are all of our superheroes out in the field making their measurements. We have at a variety of different sites, and in collaboration with the DOE SAIL program that's also going on in that area. We have scanning X-band radars, we have snow level radars, S-band radars, a bunch of surface flux stations, surface met, the clamps trailers out there profiling lower atmospheric structure. We've got the UAS, a bunch of flux towers like the sky. So it's a really heavily instrumented area over a few miles of distance in the East River watershed, just north of Crested Butte in Gothic. And we're targeting processes that are important for hydrometeorology. Splash is the study of precipitation in the lower atmosphere and surface for hydrometeorology. That's the acronym. Trying to understand the forcings for our hydrologic models. And all this water, by the way, goes into the Colorado. Colorado is a huge thing right now. Clearly, from a climatic perspective, we know that there are some water scarcity issues that are coming down the pipe. And for the Mountain West, and particularly for the Southwest, the Colorado is hugely important for supporting the livelihoods of a lot of different people down there. So trying to understand all the physics that go into what drives water and stream flow in that part of the world. Awaken and Arise, these are projects that are being developed to understand wind energy impacts on lower atmospheric structure. So you get these wind farms set up. This one's in Oklahoma, but Iowa, Texas, there are a lot of places in the Midwest where we're getting a lot of wind turbines, which is fantastic to see. But those turbines do have impacts on the downstream flow. And so there are important questions about what those impacts look like, as well as how we can do this most efficiently. Because as you transition back in the wind farm, each one of those turbines becomes a little bit less efficient with the amount of momentum that's sucked out of the atmosphere upstream. And so we're going to leverage the Raven, hopefully to fly transects within the wind farm and understand how those wakes evolve under different environmental conditions, and better be able to position both the turbines themselves and downstream assets. And then on the technological innovation side, there are a few projects that we're trying to undertake. One is adaptive sampling. So these platforms, when we send them up in the atmosphere, we usually put in some waypoints and we say, go fly over there, and they go do it. We don't have to fly the aircraft other than by watching it and telling it where to go. But there are different ways to do this, and there are groups in France right now that are developing algorithms to have the aircraft decide where it needs to go. And so leveraging the environmental conditions that are being observed around the aircraft and by the aircraft, and saying, okay, here's a convective core. Let's try to optimally sample that based on what we think is an optimal sampling technique. Go ahead, airplane, you go fly and come back in 2 hours. right? And the airplane pops out of one side, decides it's left the convective core, does some onboard processing, turns around, comes back, samples the core again, looks for the next pass, and just does that for a couple of hours to sample that core. I mean, it's pretty early for stuff like this, but you can think of boundary layer features, pollution plumes. There are lots of different types of features that you might want an airplane to sample without you having to decide this is the optimal way to do it, looking out in the atmosphere and not really knowing where that plume is. The aircraft is making the measurements, so it should know as well as we can. And then always working on instrumentation. We have our Blacksmith probe right now that we're using. There's some things that work very well with that probe. There are other things that don't work quite as well. We're working to develop a new multi-hull pressure probe, 9-hole probe, that will hopefully lead to even better wind measurements than we currently have. And it's just an example. I mean, the instruments are key to everything we do, so we're always trying to advance those. All right, so a very quick summary. I won't read all the words, I promise. But generally, we're using small UAS to provide new perspectives on a wide variety of atmospheric phenomena, or science phenomena, and better understand what's going on in the lower atmosphere and how that interacts with the surface. We've deployed these systems all over the world, from the tropics to the poles, both hemispheres, to try to document kinematic, thermodynamic state, aerosol properties, etc. We've got a variety of different current projects that are ongoing, connected to the Arctic boundary layer, understanding tropical trait cumulus, mountain meteorology with SPLASH. The assimilation question is still an interesting one, and I think one that we're barely scratching the surface of. And I could talk for a long time about where I see really good opportunities for UAS to contribute to our weather prediction capabilities, namely as commercial operation of these types of systems accelerates, which I think it will. We need to replicate what we're doing with commercial aircraft in terms of collecting data, particularly for areas where we would likely have a high density of operations but don't have a lot of measurements, which is low altitude over rural areas and low altitude over urban cores. We have no real observing networks looking at the boundary layer in those situations because you've got a few radiosondes set up and aircraft that are spending about 30 seconds in the boundary layer before they're beyond it and moving out. Whereas these aircraft would be spending a lot of time down there and providing really valuable information. Surface property evolution from a different variety of different systems and over a variety of regimes. Talked about the wind turbines and the wake effects, and then all the different technological advancements that support this. Most importantly on this slide, I think the last bullet, which hopefully the people in the back can read on the screen, but we are very much open to finding collaborators who think that their science might be able to benefit from some of the things that we're doing. And if you see this sort of technology and you say, hey, that paper that I was writing could have been a little better if we had these measurements, come talk to me, right? To find those opportunities, because I think, again, Grant and I were talking earlier about these types of capabilities and how they might support science. And there is kind of a boundary to entry, I would say. There's kind of a challenge that getting these platforms up and running, getting the instrumentation right, working with the FAA to get all the appropriate permissions to fly in the way that you want to fly, all that takes a lot of energy and time. And while it's really great to think that everybody can just go out and do this, the reality is different. And even for me, I benefited from decades of previous experience at the University of Colorado in doing this. And I'm just carrying it forward in a different way. But it is not the easiest thing to just kick this off and go out and fly something. And so this is the sort of instrument and facility where it makes a lot of sense to find people who have done this in the past and at the very least can help you get started and get going down the right path, but potentially, if it makes sense, also do some of the flying and operations for you. So if it's interesting, come talk to me, and I'm happy to explore what possibilities might be out there. So I think that's it. I've got some references, but thanks very much for your attention, and thanks for letting me walk and stumble through my first presentation in a year and a half. I appreciate that.
This is all very interesting, and we have time for a couple of questions, I think. starting maybe with students that might have questions.
For moderators who want to evaluate their results against the observation, what's the data availability?
Yeah, so it does vary a little bit by campaign, but I will say for myself, I've always done my best to make the data publicly available as quickly as possible. Depending on which campaign you might be interested in, I can tell you exactly where to go get it. Almost all of the output from these campaigns, it has been put in an NCDF format, put out in a public archive somewhere, and documented with a data paper. So a lot of the references you see here are Earth system science data papers that describe exactly what we did and why we did it, and where we can find the DOIs and the data.
Any other student questions? Okay, I'll open up for general questions.
There is a talk from YouTube. Norm Wood asks, he says, "Hi guys, nice talk. Not sure if the chat is being followed. Well, it is. But how suitable or acceptable are UAVs now for operation within cold, cloud, and precipitation, or outside of visual control?"
Yeah, that's a really good question. So I think when he's talking about cold cloud, he's primarily worried about mixed phase clouds, but Norm, please correct me if that's not the case. There are icing concerns like with any other aircraft, right? No aircraft really wants to spend significant amounts of time in supercooled liquid just because of how that can negatively impact flight. Larger aircraft do have the advantage of active de-icing systems, and so that's something that DOE in particular has tried to get to for some of their UAS platforms, but it hasn't been super successful, I would say. I haven't heard of the successes. Maybe they're there, but I haven't heard of them. What I will say, though, is we have flown these aircraft through clouds in cold environments. We've always survived, and this is kind of where that risk-reward trade-off starts to come into play, where some of these smaller, lower-cost platforms, you might be okay sending one of those in an environment where it might not fare well, assuming you can demonstrate that you can do it safely, and try some of these things. So for the Data Hawk, for example, that's a platform that we've sent into cloud many times, because if something did not go well, we were confident that we can do this in a safe way, and if the aircraft did come down, it wouldn't hurt anybody or anything. So I think that's where the small UAS do have this advantage of being able to go into environments where, again, other aircraft may not want to spend very much time.
Brad?
When you're, for the Mosaic campaign where you're looking at the melt ponds and the different albedo, did you have flux measurements along with that? And did you see that same collapse to kind of a homogeneous flux as you go up? Or?
So we didn't have, when you're talking about flux measurements, you're talking about turbulent fluxes?
Turbulent flux.
From the UAS.
Yeah.
We didn't from the UAS for that campaign. We are actually, we didn't fly the Raven for that campaign, and that's the one where we can get our vertical velocities pretty accurately. For the Data Hawk, we don't have a good vertical velocity measurement. We're going to try some different approaches for calculating fluxes with gradient methods and other things. I don't know how that's going to work out. I haven't done that before, but we'll give it a shot. And I would say that it's a good question of how the fluxes react. We definitely had flux measurements at the surface, and with the 20-meter flux timer that was in place, we might be able to leverage a 20-meter tower a little bit to see whether there's a clear gradient. I would suspect that there is, although some of that is going to be governed by the scales, the turbulence, and the eddy scales that are coming up over that ice surface. So I don't know. I haven't looked at it.
I'm just curious about some of the other applications. Has this fared well in restaurants?
Yes.
Okay.
Yeah, very well. Actually, so both the Raven and the Tempest, which was the yellow-winged aircraft that was flying into the severe weather,
Yeah.
those have both been used specifically to sample gust fronts around supercells.
Mm-hmm.
And both of those are set up to be able to fly in bursts at very high speeds, pushing 80 to 100 miles an hour, depending on the airplane, so that they can recover in case winds pick up drastically and push it the wrong way. So we don't like to fly at that speed because it really impacts our endurance a lot. But the airplane is set up to cruise at 17 meters per second and burst up to 40 or 50 meters per second. So it can tolerate that. It just won't be able to do it very well.
And just an application question on that. Would you foresee that being applicable over like the tropical ocean, like from a
Tropical
shipboard?
ocean?
Yeah, from a shipboard, like that would be feasible.
Not those platforms specifically,
Okay.
but, so the vertical takeoff and landing platform would be very suitable for that sort of an application, and again, that was what we were going to do with Atomic until they told us the aircraft wasn't ready. With that aircraft, it's not our airplane, so I'm not sure what the top speed is and what sort of tolerances it has for hitting a sudden wind gust, but,
Okay.
you know, I think for all those things, I want to say it would be okay. I'd have to dig into the numbers a little bit and better understand what scale of gust front we're talking about.
Thanks.
Kind of related to that, thinking about like the open ocean and repeat hydrography, how useful would something like this be on like a typical station section where you're blasting across the Pacific, let's say, and measuring at stations that are very, very far apart in comparison to the scales at which you're measuring? I'm just wondering, like, I'm sure people you and Noah and lots of people have thought about this, so I wonder if you could speak to that a little bit.
Yeah, it's a good question. I will say that the most successful campaigns we've done involve staying in one place and doing the same thing over and over and over again, so we have good statistics. But I think that for something like what you're talking about, if you're going, and I assume I'm understanding this correctly, but if you're on a research vessel and it's going across the Pacific and you're doing a flight here and a flight here and a flight here,
Yeah.
I think that can provide very useful information. And the other thing I will say with that sort of a setup, or with some of the land-based operations, these aircraft tend to work well in partnership with surface-based instruments. So for a research vessel application, you know, having the kind of local near-surface meteorology as the airplane's up and flying,
Yeah.
and specifically for this vertical takeoff and landing platform, that is set up to fly for 3, 4, 5 hours at a time. So things can evolve at the surface quite a bit, especially if you're moving across, you know, an ocean eddy or something like that. So to me, I see value in looking at the spatial variability over the length of a cruise, but I think it really depends on your research questions and what it is you're trying to address.
Great.
Yeah, do you have a kind of a pet theoretical hypothesis you're trying to prove with all this data?
It depends on the project. So for the Arctic deployments, specifically Erasmus and the early campaigns, I was really looking to address some of the open questions, specifically related to aerosol transport, right, from some of the work that we did a long time ago, and thinking about whether the surface-based aerosol measurements that we have meant anything for aerosol cloud interactions at cloud height. So that was one of the primary objectives there, was to map out the vertical structure of the lower atmosphere and the aerosol transport through the layer, and better understand when we can connect our cloud to the surface. So we used those data as well as the observatory data to do a long-term analysis of aerosol cloud interactions and look at the impacts of aerosol concentrations on the long-wave emissivity of the clouds. And that was actually quite successful. So that's one example for that campaign. But you know, we're all over the globe. So
let's say from that,
vary.
you have a bottom line of how you contributed to the overall understanding. I know you did a lot of observations and you found,
Yeah.
but what is the bottom theoretical result that you have that you now can say changes how we think of these Arctic clouds, for instance?
Right, so for the Arctic clouds, I just gave you the example of the aerosol cloud interactions and better understanding the mixing state relation to aerosol mixing and whether those are equivalent. They're not always equivalent. But for another example with stable boundary layers, right, so understanding these kind of frontal structures that are advecting through the stable layer, what's driving those, and whether we can represent those in our simulation tools.
What's unexpected and different that you now see that you didn't know before?
We've never really had the resolution at 10-meter scales to observe these sorts of features, right? We haven't had profiling that allows us to see in high resolution these structures transiting through the stable boundary layer. And we've seen it in really, when Peter's running really high simulation LES, or really high resolution LES, all of a sudden he sees these things, and you have to start wondering whether that's a model artifact, right? Is that real? What's driving those structures? Do we see this in reality or not? And if so, what is the driving force that's creating this mixing that has this intermittent structural component to the stable boundary layer? So that's another example. I think a lot of the work related to atomic and Mosaic is just getting underway. We collected those data sets about a year ago, so the analysis there is just starting. But
What I'm looking for, though, is something we now know that we didn't know before,
right.
which is, I mean, you're saying the structure of, but what's unexpected about the structure of these things? Is there something that you've revealed from this
Yeah.
that's novel, that really,
So on the stable boundary layer question, I think the thing that we're working towards revealing is what is forcing those structures to be there in the first place. And in this particular instance, we're seeing a lot of association with the base of the low-level jet and the shear layer that exists in that place. So for the aerosol cloud interactions, what we were demonstrating is that even if you have stratified conditions in the subcloud layer, so you have perhaps a surface shear-driven mixed layer inversion and then a cloud-driven mixed layer, sometimes the aerosol properties are uniform through that whole layer. Right? And so trying to understand, again, when we have a surface-based aerosol measurement, whether that's applicable to what's going on in the cloud or not, those sorts of observations are not something we had in the past. And they provide really clear insight into how to connect the thermodynamic structure to the aerosol properties from the surface to the cloud.
Any more questions from the audience? I'll ask one of my own. I've got a lot that I'll save up for later, but the one that I wanted to just quickly ask about is you mentioned the Black Swift multi-pole port probe several times.
Yep.
What is your general impression so far of the value of the pressure-based multi-hole ports for measuring turbulence at relatively low speeds? Because it's this U-squared dependence that kind of makes the pressure signal kind of noisy at that low speed. Are you finding that they're doing a reasonable job? Because
Yeah.
that's why we've been kind of biased toward like a sonic anemometer, because it seems to work better at low speeds.
Okay, yeah, so we have looked at the spectral density from these probes, in terms of both the pressure fluctuations or the alpha and beta spectral response. And both for alpha and beta, as well as the ripple velocities that we're deriving or the U and V velocities that we're deriving, we do see a very clean response, I would say. There is a little bit of magic that goes into that when you're fusing together the information from the probe with that from the IMU and other pieces. But in general, we've seen a very nice expected 5/3 decay. We've seen good response down to about 50 hertz. And there is a little bit of a noise question. One of the things that I don't like about that particular probe is that at least the version that we have has some temperature sensitivities relative to the actual sensor, the transducer temperatures. And that does come into play as we're profiling through a kilometer of atmosphere.
Probably more for bias though, right?
Well, no, it's challenging because the sensors don't all have the same response, and it's not linear. And so we have to calibrate on a probe-by-probe basis, or we have to model what that response might be inside the housing of the probe. And we're trying to apply those corrections so that we get what would be a flat response if there were no pressure fluctuations or whatever. But to answer your question, the low speeds have not been an impact for what it is we're measuring.
Thank you. Thank you very much again for